And so we're back with part two, deterministic operations research. And so we had left off here by saying that, basically through this knowledge that we've now gained, we think we will be able to build mathematical formulas for the successful implementation of decision making tools, right? And so we're going to use this modeling process to contribute to those results. Now, what I on the right, you have this big picture approach, right? We have a problem formation. We want to build a model, collect the data, analyze the data, make sure that we've coded the model appropriately, and verify that it's working, that our results are measured with actual real output that matches our expectations. If there's a gap, we want to continue to go back and modify that approach and analyze the results. Now, on the left are things that I think will be useful for you. So you want to identify the input and decision variables, and you'll find some conversation about that on page 5 and 6 of the book. We'll go through their cupcake example in a minute. Then you want to identify the constraints. You'll find that on page 6. You want to identify the objective function on page 7. That's discussed. And then we'll learn to graph them. We're not going to do a lot of graphing this week. So, for example, here is that same approach, 1 through 4, laid out for you, right, in a linear programming problem. So, for example, if I want to maximize or minimize something, I'm going to create this linear function. And that's going to give me my objective function. I drew an arrow to it called f of x. That's going to be my objective function. And notice it's going to have my variables and constraints relative to that, right? So you see I have variables there. And I'm going to take that objective function and make it subject to the constraints put on my problem to satisfy certain points that I will graph. And those are called feasibility points. So, for example, so let's go down here. So this is it all laid out. Here's your objective function. You either maximize something or minimize it. You'll have your decision variables, and you will be subject to any number of constraints, right? Here's an example. And then in the graph, we will have our feasible solution. And the optimal solution is at one of the points in the graph. We'll talk about that. So beginning on page 5, they do an example where they're going to determine how many so they have a cupcake, a cake factory that makes chocolate and vanilla cakes, and they want to decide which are more profitable. So notice on page 5, the decision variables, they call variable C equals the number of chocolate cakes, and V are the number of vanilla cakes to bake. We still don't know how many. But now we know that was point 1. We determined the problem, right? How to maximize what's the best solution or how many cakes to make in a given amount of limited resources, right? So once I determined the problem, I put it in English, just in normal words is what I'm saying. Then I define the variables, right? And which helps me further define the objective function, right? And so the input variables are these input parameters is another way of saying it, right? And so items such as the baking time, the amount of eggs or flour, right? These are input parameters, and they're usually fixed, right? Then I have to determine the constraints of the problem, right? And so some constraints are variable and some are general, right? So a general constraint, you will always list that the item must be greater than 0. So chocolate and vanilla cakes must be greater than 0, because every one of these linear functions has as a rule a common variable bound that it's non-negative, called non-negativity, right? And so we define these variables and always create that one constraint that it's greater than or equal to 0, right? And so we can see in the problem that they've laid out the constraints, right? The number of eggs has to be less than or equal to 32, right? And notice that that's an inequality. It's not equal to 32, it's less than or equal. So it's an inequality, since we don't necessarily need to use every available egg. And so we're going to write these constraints usually as inequalities. The constraint restricting the number of eggs is, so you have 4c plus 2v is less than 32. So right now we want to make 4 chocolate cakes and 2 vanilla is what the instructions were. And they have to be less than 32 because they have to do it in less than 32 eggs. The 4 and the 2 were in the instructions in example 1.1 on page 5. Notice that it's each chocolate cake sold should give a profit of $3 for each vanilla, or for each chocolate, and $5 for each vanilla. That each chocolate cake requires 20 minutes of baking time and uses 4 eggs, and the other cake uses 2 eggs. And that's how we got that formula for eggs was 4 chocolate, because I used 4 eggs in the chocolate cake, 2 eggs in the vanilla cake plus 2v must be less than or equal to 32. I can do the same for flour. We know we have a constraint of flour to be less than 40 pounds used, right? And I know that in the chocolate cake, I use 4 pounds of flour, and in the vanilla cake, I use 5 pounds of flour. So that formula comes out to be 4c plus 5v is less than 40, etc. I also have a time constraint, which the book lays out for us. And at that point, I'm ready now to identify my objective function, right? And that's what we want to maximize or minimize, right? So we can maximize, we want to maximize the number of cakes in terms of revenue or dollars, right? So that actually turns out to be maximize 3 Charlie, because remember it was $3 that I'm earning per chocolate cake and $5 per vanilla cake. So it's 3C plus 5V, and I want to maximize that. And you can see that on page 7. And there I have my linear function, right? So my linear function is to maximize profit. So I want to maximize 3C plus 5V because I know I'm making $3 per chocolate cake and $5 per vanilla cake. That's my objective function. And then such that I want to list the constraints. So I list the constraints for the flour, for the eggs, for the time, and of course the constraint that chocolate and vanilla must be greater than 0. So I had 4 constraints. So when I do all that and I can throw in some trial and error numbers, I'm going to be able to graph them. And that's really not part of this week, but it's part of the long-term solution that we'll talk about. In week 2, I'll ask you to demonstrate areas of the graph. So if you look on page 9 of the book, the filled in area, so all these constraints create lines on the graph. And when the lines intersect, I end up with vertices. And at the vertices, at the end of the graph, we can find the maximum or minimal values. That's where they're at. In any of the shaded area, the area that all the constraints agree with, is called a feasible range. It's feasible. That would work, all right? And you have some good definitions of the solution, the feasible solution, the feasible region, all on page 8. You'll want to review that too. And then the next few pages cover graphing. which we'll save for another time. And then they go into some common classes of mathematical problems. Notice that the linear program that we are developing, this optimal solution, right, this objective function, can also be in the form of a nonlinear program. So one of the strengths of linear programs is that they are well understood mathematical problems and easy to solve. The problem, though, is that not all math programs can be solved this way, right? And so sometimes we use non-linear programs, right? Where the linear programming ideas are sometimes violated. We're going to avoid that for the most part in this course, because in the end, computers will do a lot of this work. But by taking this course, we're not only able to think through a problem differently, but before we go to the computer, right? The computer is only garbage in, garbage out, right? So we have to know what we're putting into it. We have to be able to define the variables, define the problem, which means then define the objective function, and understand the constraints. That's really the focus of this entire course. So, for example, I will stick with integers. And so these are integer programs, right? These are the most common types of linear programs, are integer programs. And so typically the variables have integer values, 1, 2, 3, 4, 5, 8, 10, right? They're not fractions. And so we make this assumption in the work we do. Now, we know that's not always the case, but I can't have half of a hot dog or half of a cake, right? A lot of times we just round up. So that's kind of how we'll deal with that. But that's integer functions. And that really wraps up chapter 1 for us. So stick with this format. Like I said, go ahead every time you do a problem. For homework, I want you to identify clearly, these are for points. I want you to identify some very key aspects. I want you to identify the decision variables, make a note of that in your homework. Just identify the constraints, the objective function along the way, and that will help get you points on all of the mathematical problems. And then in week 1, so you'll want to define, based on the problem I present, an objective function and the constraints and decision variables. Now, I have on the link to the website this week, Mario's Math Tutoring. I love Mario. I think he's great. And so this is a link here, but I'm just showing you. Go to the website for the course. You click on the link. Mario walks you through a linear programming example, and he's great. You will enjoy that too. Now you have my expectations, and we've discussed chapter 1, and you have Mario's input, and I will see you online. I'm looking forward to it. Thank you all.